Hello everyone, my name is Khizr Hussain. I'm a computer science PhD student at Virginia Tech. Today I'll be presenting Beacon, directed graybox fuzzing with provable path pruning by Huang et al. From the Hong Kong University of Science and Technology. The paper was published at IEEE SMP 2022. I've structured this talk in 6 parts. We'll start with some background on fuzzing, what it is and why it matters. Then we'll look at the specific problem this paper tackles, followed by Beacon's core insight and a detailed walkthrough of the methodology. After that, we'll go through the evaluation, and I'll wrap up with my own take on the paper's strengths and limitations. So to set the stage, what is fuzzing? At a high level, it is an automated way to find bugs in software. You take an input, randomly mutate it, flip some bits, insert bytes, change values, and feed the result into a program. Most of the time, the program handles it just fine, but every now and then, a mutated input triggers a crash, a hang, or a sanitizer violation, and that's a bug. What makes modern fuzzing powerful is the feedback loop. When an input happens to trigger a new code coverage, a branch that has never been taken before, or a function that hasn't been called yet, the fuzzer holds onto that input and keeps mutating it further. Over time, this lets the fuzzer evolve its way deeper and deeper into the program's behavior. This is a surprisingly effective strategy, and open source fuzzers like the Google Open Source Fuzzing project have found tens of thousands of real bugs in production software using exactly this approach. Now, within fuzzing, there are two fundamentally different paradigms. The first is coverage based or coverage guided fuzzing. Tools like AFL, AFL++, and LibFuzzer, they treat every part of the program equally, and the goal is to maximize code coverage. That is to say, explore as many branches and paths as possible, without prioritizing any particular location. On the other hand, the other paradigm is directed fuzzing. Here you have a specific target in mind known beforehand. A known vulnerability, a patch you want to test, a crash you want to reproduce, and instead of exploring everything, the fuzzer focuses its effort on reaching that one location as fast as it can. AFLGO, Hawkeye, and Beacon all fall into this category. The distinction is important because in a lot of real world scenarios, we already know exactly where in the code we want to reach, and spending time exploring unrelated code is just a wasted effort and it costs us time and money. And there are several scenarios where this comes up. Patch testing, for example, a developer pushes a fix for a CVE and we want to verify the fix is actually complete, or in case of vulnerability production, that given a bug report, we need to generate a concrete input that triggers it. And especially with cache reproduction, a failure gets reported from production and we want to recreate it locally for debugging, and for also information and flow analysis, checking whether sensitive data can propagate to certain program points. In every one of these cases, the target is known ahead of time, which makes directed fuzzing the natural fit. So how do existing tools handle directed fuzzing, and where do they fall short? On one end, we have directed white box fuzzers, tools built on symbolic execution like Dart and CLE. These build up symbolic path constraints and solve them with SMT solvers, which in theory can guarantee reachability. If there is a feasible path to the target, symbolic execution will eventually find it. The problem is scalability. The number of paths grow exponentially at every branch, and constraint solving is very expensive. So in practice, directed white box fuzzing has been shown to be unable to reproduce known vulnerabilities even within 24 hours. On the other hand, directed grey box fuzzers like AFLGO and Hawkeye are much more practical. AFLGO computes a distance metric on the control flow graph and prioritizes seeds that are closer to the target. Hawkeye refines this with call trace similarity, and FuzzGuards takes a different angle and trains a machine learning model to predict whether inputs are likely to satisfy path conditions. All of these tools are fast and they scale, but they share one critical weakness. They only prioritize which inputs to run first and never actually reject or prune a path that cannot reach the target. They don't have the ability to distinguish between what will lead to a target and what won't. Every input gets the same fully executed priority, even when there's zero chance of it reaching the target code. And that leads us directly to the problem that this paper addresses. The authors measured just how bad this is. They ran AFLGO for 24 hours on 4 real CVEs and tracked what fraction of executed paths were infeasible, meaning they had no possibility of reaching the target. The results are pretty stark. CVE 4491 shows 98.5% infeasible, 6131 96.2%, 5969 97.8%, and 8397 98.8%. Across the board, more than 95% of all computation was spent on paths that were completely useless. The fuzzer was burning through its time budget, executing millions of inputs that could never have reached the vulnerability. This is what the paper and other literature call the infeasible path explosion problem. Beacon's idea for solving this is actually quite elegant. Instead of just prioritizing seeds and hoping for the best, what if we could determine before fully executing a path that it has no chance of reaching the target? Then we could terminate it immediately and redirect that computation toward paths that might actually work. The way Beacon does this is through three components working together. First, a lightweight static analysis runs ahead of time and computes preconditions, conditions on program variables that must hold at various points in the program for any execution to have a chance of reaching the target. Second, these preconditions get compiled into simple runtime checks, assert statements inserted directly into the binary. During fuzzing, whenever an execution violates one of these checks, it gets killed directly on the spot. And third, and this is what makes the approach very trustworthy, the preconditions are provably sound. They're they're all over approximations of the true weakest precondition, which means that every path that gets pruned is genuinely infeasible. We might miss some infeasible paths because of our analysis being conservative, but we will never accidentally discard one that could have actually reached the bug. The net effect is that instead of wasting 95% of computation, Beacon catches about 83% of infeasible paths early, before they even burn through any of the significant resources. Let me walk through a concrete example to show how this actually works. The paper uses a small code snippet where the target is a crash at line 19, which is guarded by the condition w greater than 10 at line 18. So any execution that reaches the crash must have w greater than 10 at that point. The interesting part is what happens earlier in the program. At line 9, there is a branch on x less than 20. If that condition is true, line 10 executes w equals to w minus 15. If false, line 12 executes w equals to negative w plus 15. So w gets modified before it reaches the check at line 18. Now, Beacon works backward from the target, starting from the requirement that w should be greater than 10 at line 18. If the execution came through line 10, w was set to w minus 15. Then for the result to be greater than 10, the original w must have been greater than 25. If it came through line 12 where w was set to negative w plus 15, then the original w must have been less than 5. So the precondition on w at the program entry is w should be less than 5 or w should be greater than 25. Any value of w between 5 and 25 is provably infeasible. No execution with w in that range can ever reach the crash, regardless of what other variables are. Beacon inserts the assertion w less than 5 or w greater than 25 near the entry point, and any execution that fails this check gets terminated immediately, so no time is wasted running through the rest of the program. It's a simple example, but the same principle extends to real programs with more complex control flow, many variables, and even deeper call stacks. Zooming out of the full architecture, Beacon operates as a two-phase pipeline. The first phase is offline. Given the program source code and target location, a static analysis computes preconditions. This module performs reachability analysis on the interprocedural control flow graph, followed by a backward interval analysis with two precision optimizations that I'll cover in detail shortly: relationship preservation and bounded disjunction. The second phase takes these preconditions and compiles them into instrumentation. Assert statements injected directly into LLVM bitcode alongside standard coverage instrumentation. The output is an instrumented binary that plugs into any fuzzing engine. You can pair it with AFL, AFLGO, AMOPT, whatever you prefer. During fuzzing, the precondition checks run automatically and terminate the infeasible executions with negligible overhead. The static analysis is a one-time cost, and the instrumented binary works with any fuzzer. The two phases are completely decoupled. The first step in the analysis is the simpler one: control flow reachability. Beacon walks the interprocedural control flow graph backwards from the target and identifies every basic block that has no path to the target at all. At each one of those unreachable blocks, it inserts an assert false, so that any execution that wanders into unreachable territory gets terminated immediately. This handles the structurally obvious cases efficiently, but plenty of infeasible paths still have a valid control flow path to the target. They're infeasible not because the graph structure, but because the runtime values of their variables make it impossible to satisfy branch conditions along the way. Catching those requires reasoning about program state, which is what the backward interval analysis is designed to do so. This is the core technical contribution of the paper. The analysis starts at target location with an initial precondition of true and propagates backwards through the control flow graph. At each point, it computes necessary ranges of variable values, intervals that must hold execution to reach the target. So for the condition w greater than 10, it derives that w must be in the interval 10 to positive infinity. From x less than 40, x must be in negative infinity to 40. Each branch condition encountered during backward propagation contributes a constraint that tightens the interval for the relevant variable. The key design choice here is the interval domain. It's one of the cheapest abstract domains in abstract interpretation, and the analysis is fast, scaling to real programs without difficulty, and equally important for a fuzzing context, the runtime check it produces are trivially cheap. Each check is just a comparison of a variable against constant bounds. There's no constraint solving at runtime, no complex reasoning, just comparison. That's why the instrumentation overhead averages only to 5.7%. The analysis is sound, meaning it computes an over approximation of the true weakest precondition, which guarantees that every prune path is generally infeasible. So that the trade-off is such that the trade-off is the interval domain is coarse. It may fail to prune some paths that are actually infeasible, but it will never prune paths that can actually reach the target. And that's the property that matters more for correctness. That being said, plain interval analysis has a well-known weakness. It tracks each variable independently and doesn't capture relationships between them. Beacon addresses this with its first optimization, which the authors call relationship preservation. Here's the issue. Consider the expression v equals to y minus x at line 17 in the motivating example earlier. Suppose the backward analysis has already determined that v must be less than 60 and x must be less than 20. In conventional interval analysis, where we encounter v equals to y minus x, we try to derive y's interval from whatever direct constraints exist on y. But there aren't any, so y stays at negative infinity to positive infinity, completely unbounded. The analysis has effectively thrown away the relationship between v, y, and x that's encoded in that expression. Beacon handles this differently. It introduces two additional inference rules, rules 7 and 8 in the paper, that propagate interval bounds through expressions. Since v equals y minus x and v is bounded below 60, the expression y minus x must also be below 60. Now, using standard interval arithmetic, if y minus x is below 60 and x is below 20, then y must be below 80. That's a meaningful constraint that conventional analysis would have missed entirely. And it doesn't stop there. This tighter bound on y cascades forward through other constraints. The condition z less than 2y combined with the newly derived y less than 80 gives z less than 160. Without relationship preservation, both y and z would have remained unbounded, and execution with an out of range y or z would have slipped through undetected. The core idea is simple but powerful. Track intervals, not just individual variables, but for expressions that relate them, and propagate information bidirectionally between both parent expressions and their operands. The second optimization tackles a different source of precision loss. What happens when a path or when paths merge in the control flow graph? When two branches converge at a join point, their preconditions need to be combined into a single summary. The standard approach is to take the join, which for the intervals means taking the union, and this can destroy precision. Going back to the motivating example, from the true branch at line 9, the analysis drives w less than 5. From the false branch, w greater than 25. If we naively join these into a single interval, we get w in negative infinity to positive infinity, which tells us absolutely nothing. The entire infeasible region from 5 to 25, which we worked so hard to compute, vanishes in a single merge operation. Beacon's solution to this delay is to delay merging, Instead of immediately combining conditions at join points, it maintains up to tau separate conditions, a bounded disjunction, what they call. With the default threshold of tau set to 5, both w less than 5 and w greater than 25 are kept as distinct disjunctions. The infeasible gap between them is fully preserved. Of course, paths can accumulate. You can't keep every disjunct forever. When the count exceeds tau and merging becomes necessary, Beacon doesn't merge arbitrarily. It evaluates every possible pair and selects the one whose merge introduces the least precision loss, measured by a distance metric that sums the interval gaps across all the shared variables. The pair with the smallest gap gets merged and everything else gets separated. The authors experimented with different values of tau. Going from 5 to 50 only improved the filtration ratio by about 1 to 3%, but analysis time and memory usage increased dramatically, and several programs ran out of memory entirely at tau set to 50. So 5 turns out to be the sweet spot between precision and practical feasibility according to the paper. Once the preconditions are computed, the last step is to instrument the program. Beacon is selective about where it places the checks. Instrumenting every possible location would add unnecessary overhead that it wants to prevent. The program is first converted to SSA, static single assignment, where each variable is defined exactly once. This means a precondition only needs to be checked at the variable's definition point, since the value cannot change afterward. On top of that, if one variable's value is entirely determined by another, say v is just u plus 1, then only the source variable gets instrumented. This is determined through reaching definition analysis. Between these two optimizations, the overhead stays remarkably low, 5.7% as I mentioned earlier on average, ranging from about 1% for Ben-Utils to about 10%, the highest that they recorded for LR-zip, which is in the context of fuzzing running millions of executions over hours or days, that is effectively free. For the evaluation, the authors assembled a substantial benchmark. 51 CV identified vulnerabilities across 14 real-world programs. These programs span a wide range of functionality and input formats. Ben-Utils for binary analysis, Ming for SWF processing, libxml2 for XML parsing, libjpeg and libpng for image formats, libpoplar for PDF, and libav for audio and video. They compared against 5 fuzzers, 2 directed, AFL-Go and Hawkeye, and 3 coverage guided, AFL, AFL++, and AMHOPT. Every experiment was run 10 times with a 120-hour budget, and significance was tested using Mann-Whitney U-test. The headline result is that Beacon achieves an 11.50 times average speedup over AFL-Go, pruning 82.94%, so approximately 83% of executed paths at runtime. To put this into context, AFL-Go timed out on 34 out of the 51 CVs. It couldn't reproduce them within the 120-hour budget. Beacon captured and reproduced all 51. Of those, 23 were done within 5 hours and the remaining 33 within 24 hours. And those numbers include the time spent on static analysis, by the way. The speedup ranged from 1.2 times on the easier cases up to 68.5 times on the hardest ones. The static analysis cost itself is manageable. For smaller programs like Ming, it completes it under a minute, and for the largest programs in the benchmark like libav, it took about 4 to 5 hours, which is significant but still a small fraction of the time in the 120-hour fuzzing budget. The authors also compared against Hawkeye using benchmarks from Hawkeye's own paper, and Beacon outperformed it as well, giving anywhere from 3.6 times to 5.7 times speed up on CVEs 4491 and 6131 respectively, with all p-values below 0.05. One of the more compelling findings is that Beacon's path pruning works as a standalone enhancement for non-directed fuzzles too. Since the idea is orthogonal to seed scheduling and mutation strategies, you can actually bolt it into any other fuzzer. The authors demonstrated this by integrating Beacon's instrumentation with AFL, AFL++, and AMOPT. The results: AFL plus Beacon achieved a 6.31 times speedup for reproducing specific bugs. AFL++ and Beacon hit 11.86 times speedup, and MOPT plus Beacon came in at 10.92 times speedup. These are coverage guided fuzzers that weren't designed for directed testing at all, yet adding Beacon's precondition filtering made them dramatically faster at reaching specific targets, which shows that Beacon is a genuinely independent axis of improvement. The ablation study breaks down how much each component contributes. Beacon star, which does only reachability pruning, no precondition analysis, is 1.1 times to 18.4 times slower than the full Beacon and prunes 29.1% fewer paths on average. For some CVs, it can't even reproduce the vulnerability at all within the 120-hour budget. So the precondition analysis clearly carries a lot more weight. Removing bounded disjunction makes the tool 1.05 to 4.9 times slower, and removing relationship preservation 1.05 to 5.34 times slower. Both contribute meaningfully, and their combined effect is much greater than their individual, which makes sense since these two address different sources of imprecision in the underlying interval analysis. Beyond producing known vulnerabilities, Beacon also proved effective at discovering new issues. When the authors used it to test whether existing vulnerability patches were complete, Beacon found 14 cases where the fix was insufficient, the vulnerability was still triggerable despite the patch, and it also uncovered 8 entirely new bugs. Of the total findings, 10 were serious enough to receive new CV identifiers, and all of the bugs were confirmed by the respective developers. For comparison, they also ran AFLGO and only found 6 incomplete patches on the same set of experiments. Let me wrap up with my assessment of the paper. On the strength side, the soundness guarantee is the standard contribution here. Unlike heuristic-based approaches, Beacon formally guarantees that no feasible path is ever pruned. That's a strong property that most directed fuzzers simply cannot offer. The practical numbers back it up. The 11.50 times average speed up and 82.94% of the paths pruned and only 5.7% of the runtime overhead actually show that this is very feasible. The fact that it integrates cleanly with any fuzzer like AFL, AFL++, MOpt, and AFLGO shows that it's genuinely orthogonal to existing optimizations rather than a replacement. And the real-world bug finding speaks to the practical impact. 14 incomplete patches, 8 new bugs, and 10 new CVEs, that's massive. That said, there are limitations worth noting. The interval domain, while cheap and practical, is inherently coarse, and a more precise abstract domain, maybe the octagon domain, for instance, or the polyhedral domain, could potentially capture more infeasible paths, but they might come at a higher cost. The paper doesn't explore that trade off, and it would be interesting to see where the diminishing returns set in. Also, Beacon requires source code since it operates at the LLVM IR level. That means that programs available only as binaries cannot benefit from this approach. The static analysis itself can take up to 5 hours on large code bases, which might be acceptable for like a multi-day fuzzing campaign, but potentially prohibitive and might be counterproductive for shorter testing windows. There are a few other things. For example, the bounded disjunction threshold, tau, is fixed at 5, and the paper doesn't really offer a principled way to tune it per program. Furthermore, pointer aliasing is also handled very conservatively, which may reduce, in my opinion, precision for pointer heavy code. Also, the evaluation doesn't include any comparison against hybrid fuzzers like Savior or QSYM that combine fuzzing with symbolic execution, so it's unclear how Beacon's lightweight static approach stacks up against those heavier but potentially more targeted techniques. To bring it all together, Beacon's contribution is introducing a new dimension to directed grey box fuzzing. The field has largely focused on two levers, smarter seed scheduling and better mutation strategies. So Beacon adds a third, eliminating infeasible paths entirely through static precondition analysis. The approach is grounded in a backward interval analysis made practical by their two precision optimizations, relationship preservation and bounded disjunction namely, and is kept lightweight through selective instrumentation. The result is a tool that prunes about 83% of paths with provable soundness, runs around 12% faster than the state of the art, reproduces vulnerabilities much faster than AFLGO could only manage, both in terms of speed and count, and finds real bug that existing tool missed. The broader insight, I think, is that combining lightweight static analysis with dynamic fuzzing, letting each compensate for the other's weakness, is actually a very powerful and underexplored direction. And there is definitely more work that can be done in this domain. Thank you.